Hello guys, so this portion of the video is to show you how to train the neural network and how to use this trained neural network to get predictions. Excuse me. So the problem we have here, according to the tutorial, we have a bunch of wells stripped, right? So we have some historical data, in this case from 10 different wells. Now we're going to drill a new well, but we need to decide whether to complete this well or not. Because, based on petroleum economics, there are opportunity costs involved in well completion, or leaving it abandoned, or plugging it and sidetracking, whatever it is. But we need to make that decision, right? And we have some information so far. So what do we have? What is going to be our input? So, basic, simple, you're saying that we need some particular thickness of clean sandstone, right? That the well should hit that particular reservoir of, some depth. And this in well logs, you have 50% of deflection on the gamma ray curve. So your company has seen that, okay, this is how thick the clean sandstone depths are for the old historical wells, right? Now, you've also recorded your maximum porosity values, right, based on your neutron density curves from well logs too, right? And here they range from 0 to 22%. And these are also for your old wells. And now from the cuttings from these old wells, they have some that have oil show and some that have no oil show. So now that is your input values, your parameters. Now, your output parameters is that the wells, right, where you got this information, for the initial well tests, they produced some, flow values, right? So you had some values reported as 1,000 cubic feet per day as your initial test rates. And for your first 6 months, you also reported some billion cubic feet. So now those are your output values. So these are things that right? From the 10 historical data from your wells, that for your first well, for instance, you had 10 feet of clean sand that had a maximum porosity value of 18%, and that it had no show on the cuttings. Now, for that particular well, you had 129,000 cubic feet. I believe that is, 1,000 cubic feet. And for your first 6 months, you had 13 billion cubic feet. Now, that's it for all your other wells, right? Well number 10 had 22 feet of clean sand. It had 16% porosity. It had no show on the cuttings that were recovered from the well. 120,000 cubic feet per day when you did the initial test. And after 6 months, it produced 11 billion cubic feet. So this is your dilemma, right? You have data from these surrounding wells, or some nearby region, and you're going to drill a new well. Now, when you drill this new well, you want to see if you want to complete it or not, based on some parameters that you're going to use in your decision. First, train this software to know what good well data looks like. In your opinion, this is good well data, because obviously your company completed those wells and started producing from those wells. That's why you have the data in the first place, right? So you train your software, tell it what good data looks like, and then based on what you now have, you let the software tell you if those parameters are going to represent good well data or bad well data. Now that is going to be your prediction. Right? So we understand that. Now, based on your prediction, you decide if you want to complete it, or you decide if you want to abandon it. But first, you need to train the software to know what good well data means. So to get us started, let's open our software, of course. Mine is Neuro Network right there. It opens it up. Okay, so we have that opened. We just go to new, file, new, whatever name you want to give it, right? So you could say well completion, you could say test. I mean, it is whatever name you want to give it, right? Now, that is the name. So the next thing is to put in the nodes and input layer. And for this, it depends on how many training data samples you have. So in our particular example, we have data from 10 different wells, right? So data from 10 different wells, but each of those 10 different wells have 3 different sections where we have a clean sandstone depth, where we have maximum porosity depth, and where we have the third one, in this case, is a show or no show. So for each of those 10, there are 3 different layers that affect the decision of input, right? So we put in here 3. So what this means is if you have, an extra one with some geological data that is not considered in this example, and you want to add it, then that would be a 4th input layer, right? And this represents those X's that I spoke about when I was talking in the background section. So for each of your data samples, what number of variables are you using? In this case, we're using 3 variables. Now, the notes in the hidden layer it's advised to use this equation, which I showed early on about hidden layer calculation. So basically, hidden layers would be number of data points, right? Number of data points, and we divide it by the sum of our input layers plus our output layers. Now, our number of data points here is 10 because we have 10 historical wells that we are using to train our software. Our input layers, in this particular case, we have 3 because we're saying clean sand, right? Maximum porosity, right? And whether it's a show or no show. So that's 3 input layers. And for our output layers, according to the tutorial that we're using here, we have 2 output layers, which is open flow, right? And production after 6 months. So that is 2. So feed that in there, right? 10 divided by 3 plus 2, that is 10 divided by 5. We have a value of 2. So it is advised to at least start with hidden layers of 2, and you can adjust it as and when you progress. So we're going to go with hidden layers of 2. And output layer, as we know, we have 2 output layers. Our data samples, we have 10. 10. Yeah, there we go. So as you can see, this spreadsheet was just, created as we filled these columns. We have a threshold value between 0 and 1. We're just going to leave that the default value. You can spend some more time to seeing how this threshold value affects your data and results, but it's fine if it's left at 0 at this particular point. Our transfer function, which I spoke of in the background, and I could pull it up real quick just to remind us of what I was talking about. So the transfer function is this particular thing right here, right? When I was talking about how the weights are multiplied by the inputs, and then sum is reached, and if that value is above the the threshold value, it pushes it to the next phase. So the next phase is the transfer function. In this case, you're using a threshold value of 0 for default. You can change it later on if you want. So we assume that for positive, integer values, everything is going to be pushed on onto the transfer function. So that is our transfer function, and we use log sigmoid. The sigmoid is a specified logistic type curve, as I mentioned. There are other types: hyperbolic, linear, hard limit, whatever you want to use. But for default purposes, it's always good to go with the sigmoid curve. Now, obviously, we have a learning rate, right? This corresponds to how This corresponds to how the system is learning, how much weights are changed on each iteration. So as I said, right, if you have some recurrent loop system, you look at your final results and then you go back to the initial and say, okay, based on my learned experiences, let me give this weight, some fraction of x, and this other weight some. So these values, the weights, we don't actually put them in. They're determined by the software, but they're controlled by the learning rate. And again, you could go more into details when you start like playing around with some data to get a feel for what predictions start to look like. But as a good first default value, just use 0.9. And moment coefficient here impacts how much these weight values will be adjusted based on the weight changes in previous iterations. Again, a good start is 0.6. Now, maximum iterations here, right, we have two limiting factors. Either we run the iterations for, we run the software for some number of iterations, or we get to our convergence criteria. So whichever one happens first. So if you put in 10 iterations, right, and your convergence criteria is met first, that is where your training stops, right? And if you put in 10,000 iterations and the maximum iterations are met first before your convergence criteria, well, after 10,000 iterations, your training stops. Now, obviously, there's some trade-off value, right? If you want more iterations or convergence criteria, that's something you can play with. It affects, processing speed versus how much reliable data you get. Because after some point, the values stop making, the changes stop making sense. So the offset in terms of how much processing speed you're losing, it doesn't make so much sense. And you see that later when you have so many data samples, right? A huge data set with so many variables. So it means that it takes a lot of processing to go through each and every variable for each and every example. That's where your maximum iterations and convergence criteria really start to play a role, and in my opinion. And of course, you could play with that later on. All right, so now that we've entered everything on the left column, let's go to the input, right? You just click on here. For the very first column, you want to put in your column headings. So double click there. Instead of input 1, we say bead of sand, right? And hit OK, hit OK. And then input 2, you double click on it. You can write maximum porosity in this case and hit OK. For input 3, we have show, which is show or no show. 0 for no show, 1 for show. Hit OK. And for our output here, the first one is optimum flow. Oh, my bad. It's supposed to be the one on top. Double click that and type optimum flow, right? Okay. You double click that. For output 2, you type in 6 months production, so that's 6 month production. Hit OK. And I believe that's all the information we need to enter. Yep, that's pretty much it. Now, then you go to the first cell and you start putting in your values, right? So you can have a tedious process where you type in, say, the first value according to the tutorial here, we have 10, right? So that's 10 feet. Then we have 44. Then we have 32. We can do that, right? I mean, if you have all day, you could do that. Or you could just go to, you can go here, just hover the mouse over the screen. Now it says right mouse click to open spreadsheet. So I'm going to right mouse click twice, and then I have the spreadsheet. So this is where I can copy things from an Excel sheet and paste it in here, right? So what I'm going to do here is, because I don't want to type in every single digit, I'm going to go to my neural network file. Now, remember the first zip file that you downloaded? when you're trying to install this particular software, right? That's Neuro3. We go in here, we extract it again, or if you've already extracted it, that's fine. But I want to extract these files. I want to put these extracted files in my desktop for the purpose of this tutorial. Let's put it in Reservoir Engineering software. Let's put it. All right, let me just leave it here. Okay. And okay, so these files are extracted. I'm going to go to my Reservoir Engineering software right here. Should pull up. Okay, so this is it, right? You double click it, you go in. Now you see this particular folder. It's an Excel sheet that comes with the zip file. Double click it, and that opens up. Actually, don't worry about the right column. It's extra stuff that I'm just doing just for data analysis. So that opens up, the data. So what this means basically is you can have the data in an Excel sheet format, right? You can come here, 1, 2, 3 for input. Now this extra input, according to the tutorial, is extra. We don't have that. So you don't want to copy that column, right? But here and here is optimum production, initial, and 6 months production. So what I'm going to do is I'm going to copy these first 3 columns. I don't want to copy the green part. I'll tell you why in a sec. So hit Control C, go to this particular sheet, and Control V. There you go. So you have all the data copied. Then I go back to my initial cell. I go to the last 2 columns. Did I say initials? Well, I go back to the Excel sheet. I go to the last 2 columns, and I hit Control C. I go to this opened workbook. It's pretty neat. We hit Control V, and that's where we have a copy. Now these 2 columns are minimum and maximum value. You don't actually have to put it in there because it does it automatically for you, which is really cool. You can put it there if you want, and that's it. You close it so that opens. That puts everything on here, right? So now we have all the data for all the 10 wells right here. Now this is where it gets interesting, right? This is where you have to train the data. This represents what we know. This is what we want the software to learn. And from this, we want the software to be able to tell us what to expect, right? So we're gonna train it. Now, think about it. We started with, keep in mind we have 2 as a hidden layer, the very first value. You could increase this value, the higher you increase it, the better your data. But let me actually hit train. So after this, you're ready to train, just hit train. And now you have training is complete. Okay. So what do we see here? Some errors. This is basically our total normalized error, right, between the actual and the neural network predicted values. And this is our R-squared for our first layer. Excuse me, and our R-squared for our second layer. For the output section, where we have this layer, optimum flow is our first layer, and 6 months production is our second layer, right? So that makes sense. Now, there's some errors. So it is normalized values, right? And the way I understand normalized values are between 0 and 1. So as a rule of thumb, this is just how, I figured it would be a great way for me to analyze my results. As a rule of thumb, I want my sum. My sum obviously is going to be for, if I understand this correctly, is going to be for my 2 different columns. So the individual values might be less than 1, but the sum would probably be above 1. In this case, it's 2 point something. It's not necessarily wrong, but I just want to have my sum of errors value to be less than 1. Or very close to 1. That's just something that I thought made sense. If you want to go into that particular calculations, it's basically the error within your actual and your predicted divided by the square root of your confidence interval value. So your uncertainty value square. So kind of like a root mean square type thing. You can go into it more into details, but I just want that value to be either less than 1 or a little bit greater than 1. And of course, my R squared, for linear trends, the closer it is to 1, the better. So what can we do to improve on this, right? I go to my number of hidden layer. Let me type in 4. And let me hit train. And let's see what we have, right? We have a slightly better R squared value of 0.8. It's still not too good. For our sum of errors value is 1.27. For me, that's much better, right? So what other things can we do to improve upon this? Now, before we go on there, I just want to show you guys, when you right click this, the calculated 1 and 2 is what the software is predicting. So the software is taking this information all the way up to here and saying, okay, this is what I've learned. When you train me, this is what I come up with. This value of 119 is pretty close to 129, right? This value of 11.6 is pretty close to 13. So if you're just going off the values, it's pretty good, right? 129 compared to 120, that's pretty close. 6.9 compared to 11, that's pretty good, right? We have all these extra values for what it compares for, within hidden inputs and the weights and everything, which is what it assigns to. And you can actually pull up an Excel sheet and run the numbers yourself if you may, which is what I tried doing here. Had a whole bunch of stuff, but you don't really have to do all that. The basic idea here is that changing your hidden layers, of course, your number of iterations and your convergence criteria will affect the results. And of course, whenever you train it, right, every iteration will give you slightly different results because it is applying random weights to each and every input, right? The sum of the X and the WI is the value of WI for each time you train it is different. So you get slightly different values. So for the same one, 1.27, 0.8, let's hit train again. And now we have 0.87 and we have 1.3. So, I mean, this decreased a little bit, this increased a little bit, so that's slightly different. Now we have node values of 4. Let's increase that to 6, just to show you what happens. Now we have, a sum error value that is pretty small. I like this value because it's less than 1. Right, but R squared value is 0.97, which is pretty close to 1, so that's a very good R squared correlation. It tells us how good our fit is. The second layer is 0.972, which is also really, really good. Now, the problem with increasing your nodes in the hidden layer to such high values is that now your software starts to memorize the results, right? So then it's not really learning, it's just memorizing data and it's just regurgitating something. And let me tell you why this is bad. This is a very crude example, right? So let's say you just started learning arithmetic and your teacher said 1 + 1 is 2, 2 + 2 is 4, 3 + 3 is 6, 4 + 4 is 8, 5 + 5 is 10. All right, you've memorized this. You're so good at it. You really don't understand what it means. You've just memorized it. Now, if your teacher asks you in the exam, what is 1 + 4? You're like, 1 + 1 is 2. 2 + 2 is 4. 3 + 3 is 6. 4 + 4 is 8. 5 + 5 is 10. I mean, it's got to be there somewhere, right? Because it's a 1 and it's a 4. So that number might be somewhere, maybe here, somewhere. But I really can't tell you because I just memorized it. And you didn't give me 1 + 4. So I really don't know it. Now, obviously, this is a very crude way. We know that this is equal to 5, right? But I'm just trying to explain that if we have such high values, node values in our data, let's say, exaggerated to 10, we'll get really, really, really good data, right? Now, we see this as 0.5, which is really, really good. And this slightly decreased to 0.96, 0.98. These are really good values. But you wouldn't want to run a training with such a high hidden layer because then it starts to memorize. So you kind of have to play around with it a little bit, just start getting a feel for how it behaves, what values to look out for. And as long as you can justify these reasons in your paper, that is, if you use this software, I think it's fine, right? So keep in mind, processing speed trade-off with such elements such as the number of load and the number of iterations. So again, you can change this, right? You can increase it to 100,000. Let's train it and see what happens. So of course, 100,000 is way too much. Let's use a smaller value. So let's say maybe instead of 10,000, we go with 30,000, right? 30,000 here with such a high number of hidden layer. See, it takes a much longer time. That's what we meant by the trade-off with processing speed. Now imagine if you had 100,000 wells with 10 different variables, right? It's gonna take even longer. So you kind of want to keep this in mind when you're training your software, right? Now see how really low this sum of errors value is, 0.04? I like it, right? See, this is 1. It's essentially perfect, right? And this is 0.9998. It's very, very, very close to 1. Again, this is just memorizing the data. We don't want that. We want it to have some flexibility so that we can start generalizing the data and not just regurgitating, something. Let's look at the values that this baby shows us. Right click, look at here. See, 128.9, which is very close to 129, right? 13.02, which is very close to 13. Now, conventionally, that makes sense. We want this. We like this. But what I'm trying to say is we don't want our software to think this way, because now it's memorized what we've given it, and whatever results that it spits out might not necessarily be accurate, because it's, again, 1 + 1 = 2, 2 + 2 = 4, 1 + 4, well, there's got to be something in there. You know what I mean? So let's go back. I like to keep this, start with 2, but let's just keep it at 4 for now for the purpose of this. Let's reduce this all the way to 10,000. Let's leave a confidence criteria here and let's train it. Okay. Now we got 1.4, which is not too bad. We got 0.89, it's pretty close to 1, that's good. And we got 0.94, which is also pretty good, right? So now we're ready to predict results. So we hit predict. Predict, there we go. Okay, so we right click here to open it up. Now this is already gonna be there, so we just need to fill in the columns, feet of sand, porosity, show, this, that, and we will be able to predict from there. So, okay, now that we've trained the software, right, we want to say that we think, based on our initial studies, we think that we should have about 35 feet of sandstone in our well. But now we need to know what porosity values and what show, the 0 or 1, we need to make an economical decision, right? So our initial studies show us that 35 is good. What do? We go in, we have a porosity interval, right, from 0 to 22%, but 8 to 20% is pretty good for clean sandstone. So we say 35 all the way through. All right, these are 8. These numbers do not have to be exact to your input values. Remember, we used 10 historical wells. These are 8, which is fine, right? The 10 historical wells are just the number of data samples we had to train it. We could have trained it with 20, we could have trained it with 30, right? Depending on what available data was at the time. But here we have the same 35 because we think that we should have about 35 feet of clean sand based on geophysical and seismic data, and we think this is what our porosity value should be, in between 18 and 20%. And we have a matrix essentially, right? So 8-0, 12-0, 16-0, 20-0, 8-1, 12-1, 16-1, 21. Now, of course, you can have some whatever matrix you have, but you have to keep in mind that the matrix also has to correspond to the input training data. You can't have a fourth column here when you only trained it with 3 columns. It, in my opinion, it won't really know what to do with that fourth column, right? So it just makes sense that your columns here correspond to the columns that you trained it with, but of course your rows do not need to correspond, because the rows are for the training, the rows are the number of data sets that you have, and in this place, the rows represent each and every, say, permutation of what you're trying to find. So you give it this data, right? Again, we could go in and type it manually, or we could just copy and paste. So let's go to this well data here, initial here, let's open it. Forget about everything on the right. Let's go to predict. And I'm sorry guys, it's actually not here. I will go pull it up from somewhere else. Actually, I believe I can just copy and paste from this PDF. Control C, come in here, Control V, and voila. All right, we are good. So we've pasted this here. We have that. Now we are ready to predict. So we hit predict. Okay, prediction is complete. That was pretty fast, right? This is what our software is telling us. Again, how did I get here? Just right click, double, twice, and you have this data. So now we're saying that, okay, everything is 35 feet of sand, right? But for a maximum porosity value of 8 with no show, this is what we expect, right? And that is 52,000 cubic feet per day for initial production, right? Now, after 6 months, it's supposed to look like 48.4 billion cubic foot of gas produced in 6 months. And these are the values for 12% porosity and 20%, it just, it goes on like that, right? And these are the predicted values. And of course, you could retrain it and repredict whatever, but excuse me, essentially the idea excuse me, is that our software is telling us that, so this is what our results is telling us. Now, assuming your company says okay for us to want to continue with this project, 6 billion cubic feet production in 6 months is our cutoff point, right? So we say, okay, when we drill the well, we had a no-show. If we drill the well and you had a no-show, 6.5%. This is what my company is looking for. So it means my formation has to be, 16% maximum porosity value. And for that 6, if it's a show, my maximum porosity has to be 12% for us to continue with this project, right? So let's say we do drill and we have no show, and our production is, so we can see based on these values, as I said, that it's a good guide, for 35 feet, some porosity value of 16% or 12% is good based on whether it's a show or no show. It means my company, if we have these values for our formation, we can go ahead and drill it. Now let's say we actually go ahead and drill this well, and our actual data is now 25 feet, slightly less than what we have, or 28 or 20 feet, whatever it is, right? And our actual porosity value is now, say 16% or 17%. Whatever these new values are, you can just go in and add it. So let's say our actual values are 25 feet. And our actual porosity percentage is, say, 17 feet, right? And we have no show of oil. We say 0. So we close this. This is the new data, and then we hit predict. So it's okay. Let's go in and take a look. Now it's saying that since this, right, is what I actually got for the well that I drilled, as to whether I should complete this well or not, remember my decision was based on if it produced 6 billion cubic feet in the first 6 months. Look at that, 6.46 or 47 billion cubic feet. I'll tell my company, let's go ahead and complete this well. Right? So this is the power of neural network software. I trained it. I told it what it should look out for, what good well data looks like, right? And then I went in and said, okay, based on what I have, should I even drill or not, right? And then it said, cool, go ahead and drill. And then when I actually drilled it, I said, okay, these values are pretty close, 25, 17, 0. Now, should I complete it? And it shows me 6.47. And my limits and value is 6 billion cubic feet. We have a go. We can complete as well. So that should help as a rudimentary, preliminary understanding of how this works, and you can apply it again to multiple variables. You can have, obviously, the more data examples you have, the better. The system would learn, because then it could have a better understanding of what good data looks like, right? And yeah, good luck with your project.